Welcome to our discussion on the basics of polynomials. First of all, what is a polynomial? These are some examples. A polynomial is basically anything that is a string of terms where each term is a number and then some power of x, plus and minus some more stuff also of that same style. So here is the definition of a polynomial, the technical definition, with a lot of jargon and gobbledygook. Don't get confused or worry about that. Just understand the basics. The most important thing to understand, firstly, is the leading coefficient. Right, this thing right here is your leading coefficient. That's just the number, the coefficient. Right, coefficients are the constant terms that's partnered up, let's say, or attached to the largest power of x. So let's just say we have negative 10x squared plus 3x to the fourth plus x to the fifth minus 7x, let's go to the sixth. Okay. Now the definition of a polynomial would tell us that we're supposed to write this in descending order. We should have this term first, because then that's where it becomes the leading coefficient. But it doesn't have to be in this order. This thing up here is telling us that it goes from the highest power of x down to our constant term. Well, I don't even have a constant term in my example, so if you want, I'll slap a constant on the end here. It really doesn't matter. The bottom line is you don't have to have these things in order. Right? The rules aren't that they have to be in order. The example up here is in order just to help you understand what's going on. So let's take this example down here and make sure we can still apply all of these things to it. So for instance, what's the coefficient for this term? Right? It's negative 10, and that term is the whole thing, negative 10 to the x squared. Right? So each term is each piece. Right? So this is a term, and this is a term, and even this is a term. Right? So those are terms. It's just all the things that are separated by pluses and minuses. Okay, the coefficients, right, are just all the numbers. So there's a coefficient, there's a coefficient. Well, there's an invisible coefficient of 1 right there, right? This is a coefficient. Don't forget that that's negative 7. And then here's a coefficient of 10. So what's our leading coefficient in this case? Right. Let's do that in red. Now we'll do it in green. What's our leading coefficient? Well, it's the coefficient that goes with the highest power of x, right? See, it's not just the coefficients in front. So our leading coefficient is not negative 10. In this case, it's negative 7, because 6 was our highest power. Which brings me to my next question. What's the degree? Right? The degree of the polynomial is the highest power. So in this case, our degree is 6. Okay, so those two things go together. The leading coefficient and degree go together. The rest is just semantics. They talk about the constant term. We know that's 10. Descending order just means it should be going from highest power down to lowest. But I don't want you guys getting caught in the trap of thinking they always have to be written that way. They don't. Your polynomials can be written in any order you want. We just tend to write them in that direction just so that everything kind of looks the same. So your answer looks just like my answer. Okay? So here's another example. And you can see that this example up here has all of these terms. Can we identify the leading coefficient? Hopefully you're all saying, of course we can. It's the leading coefficient is the number that goes with the highest power of x. So in this case, the leading coefficient is 4. The degree of the polynomial is 7. Right? Negative 9 is our constant. So down here, if this is my polynomial, its degree is 5, right? If this is my polynomial, degree of 3, and this is considered a polynomial, it's technically a monomial, if we really want to be pedantic. Mono being one, poly being many, right? So mononomial, right? Just one nomial, one term, versus polynomials have multiple terms. So this is just a specialized version of a polynomial, and it has degree 0 because remember this is times x to the 0, right? Because x to the 0 is just 1. So the degree of the polynomial, I think we've kind of beaten this horse to death for the basic one, but we might want to take a look at something that is a little bit more complicated. So when we start adding in more than one variable, you might think that it gets confusing, but it's still just the highest power of any particular term, right? So we have 3 terms. Here's 1 term, 2, and 3. So we're looking for the highest total combined power of each term. Well, the last one, right, is a 0 because there's nothing there, right? There's no variables at all. This one is a 2 because this is power of 1, power of 1. You add those together, right? And this is a degree of, very good, 4, right? So the degree of this polynomial would be 4 because it's the highest degreed term. So if I gave you something like this, 10 x squared y z cubed plus 3x cubed y minus that's a 4, sorry, let's make it an 8 since it looks horrible, 8z squared, right? What would be the degree of this polynomial? The degree would be 6. Why is it 6? Well, this first term has a 3, a little hidden 1, right, and a 2. Put those all together, that's a total of 6. This term has a total of 4, and this term has a total of 2. Addition and subtraction of polynomials is very simple. Some of the easiest addition and subtraction you're ever going to do, because you cannot add things or subtract things unless they are identical as far as the pieces of their terms, right? The terms have to have the exact same variables in them. The constants can obviously be different, but the variables have to be the same, right? So you can add these two together because they're both x squared. So if I had, let's say, 3x squared plus 2x, that was one polynomial, and I wanted to add it to 2x minus 5x cubed, right? This is my other polynomial here. I'm going to add these two polynomials together. My 3x squared, this first term here, I'll put it in yellow, can only be added to other terms that have x squareds in them, and there aren't any over here. So it's just going to be 3x squared. Okay, now in green, my 2x piece can go with any other single, right, powers of x. So there's another x piece. So that's going to give me plus 4x. Why isn't it x squared? Well, because I didn't multiply them, I added them, right? 2x plus 2x gives me 4 total x's. And then my last piece in blue is a power of 3, and there aren't any other powers of 3, so 5x cubed, right? So it's like adding apples and oranges. You can't add things together unless they're the exact same variable pieces. So another example, if we make it a little bit more difficult, I'm going to put it up here. If you had, a 3x squared y piece, dot, 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 a bunch of other stuff, and then you had plus 5xy squared, those won't add, right? They're not the same. You would have to have another x squared y piece. So no matter how many letters they throw at you, they just got to match. So here's some examples. You guys can pause the video and look through these. Subtraction is the same thing as addition, right? You can only do it with like terms. So for instance, down here at the bottom, this term and this term have the exact same variable pieces, right? X cubed y squared. So those can go together. Multiplication is completely open. Anything can be multiplied with anything. So you no longer have to worry about terms being the same. When we're multiplying polynomials, we're often doing a lot of this, 2 term times 2 terms, called foiling, right? Foiling is first times first, and then outside. See how those two are on the outside? So there's your F, your O for outside, and then inside is the two insides together, and then last. This one times that. So that's where FOIL comes from. I just tell my students, you know what? Just start at the beginning and multiply it through, move to your next term, multiply it through. Because what happens when I give you something like this? 2x squared plus x plus 1 times x squared minus x plus 2. And now you have to quote-unquote foil it. Well, foiling doesn't work because I no longer have 2 and 2. So just be systematic, right? Take the first term, 2x squared, multiply it all the way through. So 2x squared times x squared gives me 2x to the 4th, right? Because the x squared and the x squared, you add them. Then 2x squared times negative x gives me negative 2x cubed, right? Because this is a square and this is a 1, and when we multiply our exponents, we add, right? So then we've got 2x squared times 2, so there's plus 4x squared. And I'm done with my first term, so now I move on to my next term. So now x times everything. X times x squared gives me x cubed, so I'm going to get plus x cubed. And I like to stack mine, right? So I'm stacking my powers. And then x times negative x gives me negative x squared. And then x times 2 gives me plus 2x. Done with that one. So now I move on to my last one, the constant term, and that's easy because it's just 1 times everything. So that's just going to be plus x squared minus x plus 2. And see, by stacking them, it now makes it easy to add to get my final result. I'm going to move it over a little to the left just because I'm running out of room. So I've got 2x to the 4th, and then negative 2 plus 1, so minus x cubed, right? Because there's minus 2 plus 1, so that's minus one of them. So I got 4 minus 1 plus 1, so that's just plus 4x squared. 2 minus 1, so that's just plus 1, right? So that's just one of them, plus x, and then finally plus 2. So I would recommend learning that technique of just being systematic, starting with the first one, working your way all the way through. And don't worry about foiling. Here's another example of multiplying, and in this case, just like mine, you've got 3 pieces times 2 pieces. So again, that foiling is going to get a little difficult, so it's better to just be systematic, right? Here's where they're going to talk about what FOIL means. If you want to read it, that's fine, but just, start in the beginning and work your way through. Some special products. I'm not a big fan of memorization, but if you get these memorized, it will help you save some time, but that's about it. It just saves you some time. It is nice to be able to kind of recognize when you see something of this form that it can go back to the thing on the left, and so on and so forth. So it is helpful, but don't worry if you can't memorize those things. Last but not least, these special product examples are just showing you that if you square something, you're going to get a certain type of answer. Well, they're just taking those and putting numbers to them, right? So here's something being squared where there's a plus in the middle. Here's something being squared where there's a minus in the middle. So we go back here, okay, here's something being squared where there's a minus in the middle. And if I square it, I know I square the A piece. I have minus 2 times their product and then plus the B piece. So if we go to here, we see, okay, when I square this, I get 36x squared, right? Because that's 6 times 6 and x times x. Then minus 2 times their product. Well, 2 times their product is just 6, right? So minus 2 times it gives you minus 12, and then plus this squared. So they're just giving you an example of those, two of these things with numbers. I wouldn't spend a lot of brain power trying to memorize that. Okay, that's it.